Hello again, my students. Today we are going to discuss another problem of hypothesis testing. We discussed in the previous lectures how to test hypotheses around one population mean and difference between two population means and one population proportion and the difference between two population proportions. In this lecture, we are going to discuss how to test hypotheses around three or more population means. Actually, we are going to discuss whether three or more means are equal or not equal. Are they all the same or equal or not equal? This is called analysis of variance, and in short, for simplicity, we call it ANOVA. From analysis of variance, we call it ANOVA. The ANOVA setting is as follows. Usually we have an experiment with a factor which we want to test its levels. For example, if we have an agriculture experiment and we have a factor, a variable, we call it a factor here, and this variable was, for example, the amount of water which are giving to the trees or plants, the amount of water. And we know that little water is not enough for a tree or a plant to grow. And very big amount of water also is not very good for the trees to grow. It might kill the tree or the plant. The more water might kill the plant or the tree. So we want to know which is the level of water the best for the tree or the plant. We want to know the best level of water. Is it 20 liters or 30 liters or 10 liters or whatever is the best level to have a better production from these trees, right? So we have factors. Each factors contain two or more levels. We have one factor or two more factors of interest or maybe more, and each factor contains two or more levels, like amount of three. The factor here is the amount of water, sorry, the amount of water. And the levels are like, for example, 5 liters, 10 liters, 20 liters, 30 liters. These are levels of that factor. So the amount of water as a variable is called factor, and the numbers 5 to 10, 20, these are the level. Level also can be numerical or categorical. It can be the 5, 10, 20, and so on, or can be high, medium, low. High, medium, low is not numerical. It is categorical levels, right? Different levels produce different groups. If we give little water, for example, to different types, different pieces of land, and these are groups of lands. So we give the same level to some groups of land and another same level for another different groups of land. So we have different groups, right? So different levels produce different groups. So the groups, each group is different from the others. So they are given different levels of water, for example, different levels of that factor. So we think of each group as a sample from a different population. We think of each group as a sample from a different population. If you do an agriculture experiment, we take some pieces of land in random. We cannot take all the lands in the area, but we take pieces of land, like, for example, Each piece of land is 100 square meters. Meter squared, 100 meters squared. That's a piece of land. So we have a big piece of land, and we divide them in pieces of land. Each piece is 50 meters square or 100 meters squared, and so on. So we have different pieces of land, and we draw from randomly from those pieces some pieces of land, and give this these pieces are given the same level of water or treatment, and so they form as a group or sample from the same population in that case. So we observe effects on a dependent variable or on the dependent variable. So we have the amount of water as the factor. We have levels also, 5, 10, 20. These are levels. So we have factor and level. Also, we have dependent variable. What is the dependent variable? In this case, the variables which we want to measure. Like in this case, the amount of production. So we give different level of water, and we want to see whether we have different level of production or not. We want to see whether they have the same amount of production or different. If we change the level of water, do we have different level of production or not? So we want to test whether the groups are the same. That means whether the groups have the same mean or average of production. If they are the same, then they have the same mean of production or the same average of production. If they are different, then every piece or every group has different mean of production, right? So this is experimental design. We usually here use an experimental design to collect the data. We have an experimental design, and we have different types of designs. We have different types of designs, not one single design. We have different design. Some of them, or many of them, are complicated, and it is outside this course, outside the scope of this course. We want to study in this course only one design, which we call it completely randomized design. Other designs are outside the scope of this course. That's the simplest design, is the completely randomized design. And this design, experimental units or subjects are assigned randomly to groups. Subjects are assumed homogeneous. Experimental units, what is the units? Is the pieces of land are taken randomly and given the same level. These random pieces of land are given the same level of that factor, which is a piece of amount of water. Another group of land, sample of lands, sample of pieces of land giving another level of water. Third sample of land giving the third level of water, and so on. So we have groups of lands and giving different levels of water. So subjects are assumed homogeneous. What do we mean by homogeneous? We mean that they have the same variance. We do not expect one piece of land to have very high production, and the other piece of land which is giving the same treatment produce very small amount of production. So they are around each other. So if all high are giving the same treatment, we expect to be nearly the same, roughly the same, and they give the same amount of production. So only one factor. In this case, we want to study only one factor or independent variable with two or more levels. So we want to study, for example, the amount of water only, the effect of water only. That's the one factor affect the amount of water. So we want to study for this experiment, in this our example, we want to study the water. So the effect of water on the trees or plants. So that's one factor. And this factor has different level. We want to test whether 5 liters is good, 10 liters better, or 20 liters better, or less, on 30 liters, or whatever. So we have different levels of that factor. Right, so we study in this course only one factors with different levels. Can be 2 or 3 or 4, but we have only one factor. So this experiment is analyzed by one factor analysis of variance. If we have more than one factor, then we need to study two-factor analysis of variance. But it is outside the scope of this course. We are studying now one factor, which means we want to study the one-way analysis of variance, not two-way analysis of variance, which is one factor analysis of variance. One factor analysis of variance is called one-way analysis of variance. One-way analysis of variance, in this case, we evaluate the difference among the means of 3 or more groups. I mean, we are going to test whether 3 or more means are the same, I mean equal, or they are different. So we have an assumption whether the 3 or more means are equal. So, example, accident rates for first or second and third shift, and expected mileage for 5 brands of tires. So accident rates can be high. Are they higher in the first shift or second shift or third shift? And we can measure the expected mileage, but for 5 or 3 or 4 brands of tires. So that's another example. So what we have one factors, the accident rates or expected mileage. I mean, the shift actually. The factor is the shift here, first shift, second shift, third shift. And the dependent variable is the accident rate. And the second case, expected mileage is the dependent variable. And the brands are the factor. And we have 5 levels of brands, 5 types of brands. So we have 5 levels of brands of tires. Tires, we have 5 brands. We want to test whether the expected mileage for these 5 brands are the same or different. If one brand of tires is better than the rest, they will not have the same mean of expected mileage, right? And we have assumptions to be able to test this hypothesis. One-way analysis of variance is to test a hypothesis of equality over 3 or means. Equity over 3 or means, we want to use one-way analysis of variance to test it. So in order to be able to test it, we have some assumptions. First assumption is the population are normally distributed. The figures which we get are normally distributed. In our example, agriculture experiments, these figures, which are the production, amount of production, are normally distributed. And then those examples here, in this example, accident rates are normally distributed, or expected mileage for the 5 brands, and for the whole replications here, or the random units are normal distributed, and also their variance are equal, so they are homogeneous. The population have equal variances, so the other groups are homogeneous. The third assumption is that the samples are randomly and independently drawn. So when we have a big piece of land, divided by 50 or 100 meters squared, we assign the levels for these pieces of land randomly. That's an assumption and should be valid here. Now, the hypothesis, statistically speaking, the hypothesis of one-way ANOVA analysis of variance is that the null hypothesis, which is mu1 equals mu2 equals mu3, and so on. If they have three, that's it. Yeah, if we have three groups or three levels of that factor, then mu1 equals mu2 equals mu3 if we have three levels. If we have four, then equals mu4, and so on. That's the null hypothesis, which means all population means are equal. All population means are the same. In other words, no factor effects. If they are the same, then for in our example, agricultural experiment, if you give less water or more water, you will get the same production. That's it, no problem. There is no effect of water. That's if the null hypothesis is true, then there is no effect of water. So no factor effect or no variation in means among the groups. The alternative hypothesis, if we reject the null hypothesis, then not all the population means are the same. Not all. They are not all different, but not all are the same. That means it can be two, if you have three means, two are the same, but the third is different from them. We mean not all of the population means are the same, right? So at least, that means at least one is different from the rest. At least one, maybe it's all different, but we have something different. At least one mean is different. So one of them can be better than the rest, right? Or one is better and there is a second better best and third best and so on. At least one population mean is different, which can be the best, right? In other words, there is no factors, there is a factor effect in this case. If they are different, then there is factor effect. If the amount of water given to this plant is significant, make difference, then we expect the means are different. But if the amount of water does not make a difference, then we expect the means of production for all pieces of water are nearly the same. So that's the problem here. Now, there is a factor effect in that case. So which means also does not mean that all population mean are different, but not all population means are the same, right? Observe that some pairs may be the same, some pairs may be the same, as I mentioned, right? So one-way analysis of variance again. The null hypothesis is mu1 equals mu2 equals mu3, and if you have more, then will follow. So the alternative hypothesis, H1 or HA, not all mu j, that means not all means mu j for j equals 1, 2, 3, and so on, not all means are the same, right? If the null hypothesis is true, that means all means are the same. That means also no factor effects. That means also the distribution of production, or the distribution of the dependent variable will be like that, like this. All means are the same. All have the same means here, the means, and the same variance. So the distribution of production or the factor level will be the same exactly. So like superimposed in each other, right? Now, if the null hypothesis falls, it's not true. The null hypothesis is not true. So we have at least one of the means different. So there is a factor effect. There is a factor effect, or factor effect is present. Then the distribution will be like that. Can be two means the same and one is different, or all is different, right? So at least one mean is different. So if the null hypothesis is not true, then at least one mean is different. Can be two means the same. It's okay. It's okay if two means are the same, but at least there must be one mean is different, right? In order to test this hypothesis, we have to partition the variation. How to partition the variation? They have the total sum of squares. Sum of squares is the difference between each observation and its means, and then square it. Square of the difference between each observation and the group's mean. So that's the variation. So the sum of squares, total sum of squares, which will, when we calculate the variance or standard deviation, we calculate that sum of squares and divide it by n, or n minus 1. So the total sum of squares, we divide it by two factors. The SSA, which is among the groups, sum of squares, or sum of squares among groups, we call it SSA. And sum of squares within groups, or within groups, sum of squares. So we have SST, which is the total sum of squares, total variation. We divided it into two components. The first component is the sum of squares among groups, or among group variation. And plus, SW, which is the sum of squares within group, which is within group variation, right? So the total variation is the aggregate variation of the individual data values across the various factor levels. I mean, for the whole levels, for the whole observations, all levels, we have the variation, which we calculate x, each value of x observation minus the x bar, the average, and square this difference, and we sum up all these squares, right? And then among group variation among factors, sample means, right? And within groups, variation that exists among the data values within a particular factor level. We will see how we calculate all of these sums of squares or variation. So we have total variation is T divided by variation due to factor is A plus variation due to within groups, right? Which is again we have total variation divided by variation due to the treatment and variation due to random sampling. The variation due to within groups are called variation due to treatments among groups. Sorry, variation among groups is called treatment variation or variation due to treatment. So it has different meanings, or I mean, in some books they call it something, and other books call it another thing. So in some books we call it sum of the squares among groups, or other books we call it sum of the squares between groups. On other books we call it sum of squares, model sum of squares, sum of squares of the model, or model sum of squares, or among group variation. It has different names. This is this part. And the other part is variation due to random sampling, has also different names due to different books. Sum of squares within groups, or error sum of squares, or sum of squares of the error, or within groups variation. So all these names are the same, whether this or this or this, we mean the same thing. Now, the next step is to know how to calculate all this. We want to calculate all these three parts. We are going to discuss this in the next lecture. See you again later. Bye bye.